Let's sketch a heating curve for the following substance starting at 50 degrees Celsius. Why might we want to do this? Well, if you can understand how these heating curves are created, you can understand a little bit more about both enthalpy, solids, liquids, and gases, and then also these specific heats for the substances. So this is an unknown substance, but we know certain variables about it. For instance, we know the melting point is negative 15 degrees Celsius, and the boiling point is 75 degrees Celsius. We also know our specific heats and our enthalpy values. So knowing those variables, we can figure out at what points does our substance change from a solid to a liquid to a gas, how quickly does it make those transitions, that kind of thing. So first off, we're going to start at negative 50. So we're going to start it right here. And we know that we're going to change to negative 15. So that's our first. I'm just going to do just a random slope. The slope of this line is going to be proportional to our heat hatted. But since I don't have an axis here, it doesn't really matter how I draw that. Okay? Everything else is either going to be relative to this. It's going to be more steep, it's going to be less steep, that kind of thing. And so it's going to be relative on this axis. And this axis, I'm going to try and be it as exact as, I can. So approximately 15 right there. Okay. So I'm slowly changing. What's happening here? So we go from some very low temperature up into our melting point. And at that melting point now, we are going to take some amount of energy to change from a solid, which is what is this right here, to a liquid. And so we're going to make that transition. Now, if I look at my enthalpy values and I see my enthalpy of fusion, so my enthalpy of vapor obviously is turning it into a vapor, so therefore you can kind of backtrack if you forget what fusion means, and you can realize that fusion is the enthalpy that's relating this change here between a solid and a liquid. And so it is about 1/4 of the size of my enthalpy of vaporization. And so because of that, it's going to be the smaller of the two. And so this line right here is representing an equilibrium process where your solid is changing into a liquid. The size of this tells you how much energy is required to make that change. Do you need to put in a whole bunch of energy in order to make that change? Not as much. And once again, those are related to your intermolecular forces, which we've discussed in depth in this course. So now we're going to slowly transition up to the 75, our boiling point. What's happening is all of the energy from this point to this point, all the energy is going into changing of the temperature. So you're getting temperature changes here. During this, you're not having any temperature changes. All of the energy that you put in is going into restructuring those intermolecular forces. It's going from a rigid solid to a looser liquid. And so the energy changes happening here are not related to a change in temperature, they're related to a change in the structure or the substance. But now we're going to add temperature. We're going to add more heat. What does that heat do? It changes the temperature. So now we're going to start to climb again. Now, how am I going to climb? So we had a specific heat here of 3 joules per gram Celsius. So 3.0 joules per gram times degrees Celsius, which means I need to make, for every 1 gram, I'm going to need to input 3 joules of energy to change 1 degree Celsius. My next transition is less than that, but it's pretty similar, 2.5 joules per gram degrees Celsius. So since it's about the same, my slope is just going to be just a little bit steeper, okay, because I need just a little bit less energy to make that same 1 degree Celsius jump. So it's going to be pretty similar. If I wanted to, I could pull out my nice handy little ruler, okay. So this is the slope here, but I know I'm going to be a little more steep because I don't need as much energy. So a little more steep. And then I'm going to make it all the way here to 75, so approximately here. And there is my next curve. So what's happening during this line? So once again, this line is restructuring here. All of the heat that you're adding is going into a change in temperature. And that change in temperature is dependent upon a specific heat. Okay? Whereas here, your temperature change is dependent upon an enthalpy value. So where do we go next? We've changed from a solid now to a liquid. So your substance is entirely a liquid here. Now I need to change into a gas. So how big is my flat line going to be? Well, if I look at my enthalpy values, my delta H vaporization is about 4 times the size of this, okay? Because it's 20, this one was only 5, okay? And that's kilojoules per mole. So the size of this, I need to make it about 1, 2, 3, 4 times that before I start going up. And so this here is going to be my enthalpy. That's depending upon my vaporization. This one is dependent upon my fusion. But notice how the size is larger. Then the next step is now I need to increase and turn into a gas, because all of my energy here is changing temperature. All of my energy here is turning my liquid into a gas. And so this is an equilibrium process, and so it's slowly changing, going back and forth until it's all converted into a gas. But now we're converted into a gas. Now I need to do another line. So what do I know about that? I know my specific heat for my gas is going to be 1.0 joules per gram degrees Celsius. And so if that's the case now, so my 3 was about like this. I got steeper for my 2.5. I need to get steeper still for my last transition here. And so now any temperature, any heat, that I add after this point is going to go into changing my temperature, not changing the phase. And so here I've got my phase of a gas, and I have finished this phase diagram. But the main thing is you've sketched it out, you've thought through what are the different steps, what's happening. Your solid is melting. If you go this direction, it's freezing. If you go this direction, you're evaporating. This direction, you're condensing. You've got your phase changes happening here at your flat locations. You've got changes in temperature happening between those flat regions. So that's why this is called a heating curve, is because you've got what happens to your substance as you are heating at a constant rate. But the idea is this is all kind of relative to each other, and it reminds you what is happening at each location on the heating curve.